Welcome back, my friends, to the show that never ends. We're going to be doing the atomic theory class number 4, which is going to run from, looks like number 69 to number 83. You're going to have calculator. Go get it. You're going to have your periodic table also. You have to have it. I don't know what else to say. I have mine. Look, it's right here. Something to write with. What are isotopes and why they're so important? Isotopes is a word you heard of. I don't know what's going through your head now when I say isotope. Maybe you're thinking radioactive isotope, but we're going to learn what this word means, why they're so important, and in order to do that, we're going to back up just a little bit and then catch up again. John Dalton, a very long time ago. Remember him, the father of atomic theory? He said all atoms of an element are identical. Remember I said that too. You have copper, I have copper, our atoms are identical, can't tell them apart. But he never knew about subatomic particles. He didn't know about protons, neutrons, and electrons. He knew about chemistry. He was smart. He could see how copper reacted. He didn't understand it. He thought all the reasons it reacted and did what it did was because it weighed a different amount than other atoms. He couldn't tell that some copper actually had a slightly different mass than other copper because it was too small a difference. And, you know, he was in a barn, right? He was a farmer. But there's differences. Atoms are not quite identical. All copper atoms. What he should have said, what you need to know now, is that all atoms of an element are chemically identical. They react the same way. They all have the same exact chemical properties. And as far as the physical properties, you probably can't tell the difference. Neither could I. But they are not physically identical. They're not physically identical. There's slight variations, and that's what an isotope is. It's an atom of one element that's slightly different than some of the other atoms of that element, and we're going to figure that all out right now. Normally, atoms have a certain number of protons, neutrons, and electrons. The proton number is set. That's the atomic number. The electron number is the same. So, for instance, iron atoms. Iron is Fe. Iron is right here. Iron has 26 protons. Iron has 26 electrons. There's an electron configuration that 2-8-14-2 that adds up to 26. Now, the mass of iron is 56. 56 AMUs. And if, remember that? Protons and neutrons, a whole nucleus in my hand. If 56 is the total and you take 26 away, that means you have 30 neutrons. This is where the mistake or the difference is. Some iron atoms have less than 30 and some iron atoms have more than 30. Atoms of iron, or any atoms that have a different number of neutrons, are called isotopes. Different iron atoms with different numbers of neutrons are chemically identical. They react the same way. Their mass difference is really little, but scientists measure stuff like this. I can't measure it and you can't measure it, but they're different. Now, every atom has isotopes. Every atom has multiple isotopes. Even hydrogen has 3 isotopes, and it's really little. That's why I said before, hydrogen has a mass of 1. It has 1 proton and it has 1 electron. But sometimes it has a mass of 2 because there's 1 proton and a neutron also. Sometimes there's a mass of 3, 1 proton and 2 neutrons. Those are isotopes. Now, there's 118 kinds of atoms, 118 elements, but there's almost 1,500 isotopes. And really, isotopes don't matter in a lot of ways. I mean, really, the subtle difference between copper atoms with different numbers of neutrons is too subtle for me or you. It's just a really, really special little difference. Most isotopes, probably 90% of them, it doesn't matter, you wouldn't even notice, but about 10% of them, about 150 isotopes are actually so funky, they have such a weird number of neutrons compared to normal that they become radioactive and they will emit radiation. And that's bad for living things, but otherwise you wouldn't even notice it. It took a long time till Marie Curie kind of, you know, amongst other people, helped figure out what the heck is this radiation and why is this coming about? And they started really looking to see not all polonium atoms were the same. Some of them had a different mass, and they really worked on this for a while to figure this out. So each kind of atom comes in a variety of masses, and every atom is an isotope of that element. On the periodic table, we have said we round the mass to the nearest whole number, the mass number, take away the protons is the number of neutrons. That really is only for the most common isotope. But there's other isotopes. There's lots of isotopes. So let's see what else we can learn. Neon has three main isotopes. We call it neon 20. And if you look at the periodic table, over here, neon has an atomic mass of 20.180. We round that to 20, but it's actually a little higher, right? Why would it be higher? Well, maybe some of the isotopes have a little bit of a higher mass, and they do. We have an isotope called neon 20. We have an isotope called neon 21. We have an isotope of neon called neon 22. Three different masses, 20 AMUs or 21 AMUs or 22 AMUs. Now, how many protons, electrons, neutrons, and what is the mass? Now, in the first one, the red one, neon 20, the most common isotope, because when you round the mass, it rounds to 20. That means it's the most common isotope. It's, of course, number 10, so it's got 10 protons and 10 electrons. If the mass is 20, take away 10, that leaves you just 10 neutrons, and the mass is 20 AMUs. But what if your mass is 21? What if you're an isotope of neon? You have a mass of 21. What about this middle column? Well, if you're neon, you got to have 10 protons and 10 electrons. You're atom number 10. That's the rule. Atom number 10 has 10 protons, 10 positives equal 10 negative electrons. But if your mass is 21, if the neutrons plus the protons is 21, and you take 10 protons away, now you have 11 neutrons. And the mass is higher, 1 AMU more, because 1 extra neutron. What about neon 22? Neon 22 is neon. That means it's got 10 protons, and if it's got 10 protons, it's got 10 electrons, but it's got a mass of 12 neutrons. It's 10 plus 12 is equal to 22. There you go, 3 neutrons. Now, 3 different numbers of neutrons. Now, they're not in a 1/3, 1/3, 1/3 ratio. That would be too easy, because then you could say, well, if there's neon 20 and neon 21 and neon 22, let's add them up and divide by 3. That would mean neon should have a mass of 21, but it doesn't, right? Neon 20 is by far the most common isotope. And the reason I know that is because the average weighted atomic mass is so much closer to 20 than it is 21 or 22. It's a little higher than 20 because most of it should be, well, most of it is 20, but some of it's 21 and some of it's even 22, but it's not equal shares. So it just makes what's called the average weighted atomic mass slightly more than just 20. But it rounds to 20 because we're friends, and the most common isotope of neon is neon with a mass of 20. But there are other isotopes. How would you know that? You would never know that. How could you possibly know what the isotopes are? They're not on the periodic table. They're not on the reference table. But if you see it on a piece of paper, this atom has these 3 isotopes, or these 5 isotopes, or these 2 isotopes, there you have it. So these 3 isotopes of neon are all chemically identical. They're all a gas, they're all neon, they all make orange light, they all are chemically identical. They have the same number of protons and the same number of electrons, but they have a different number of neutrons. The only difference is that their mass is a little bit different. And look at these crazy numbers up here. Let's see, we got neon 20, neon 21, neon 22. Underneath, we have those big numbers. Now, neon 20, this gets a little complicated, and I don't want to talk about it too much, but the actual mass of neon 20 is closer to 19.9924. And there's reasons for that that I will talk about another day. Neon 21 doesn't quite weigh 21, it's 20.9924. And neon 22 has an atomic mass of 21.9913, but we're friends. Yeah, we're gonna round them. Now underneath, it's proportional. Of all the neon that scientists have found so far, they're convinced that 90.48% of it is the first kind, neon 20. And only 0.27% is neon 21, which is kind of a less common. And then the last one, still only a little more than 9% is neon with a mass of 22, with that extra 2 neutrons. All 3 of these, though, are stable. That means they're not radioactive. So there's 3 isotopes of neon. They make up all of neon, 100% of it. So let's see, I'm gonna add this up. I'm not even sure, but I should have done this before, but let's see what it adds up to. I'm adding a 90.48 plus 0.27 plus 9.25, and that gives me, can you see it? Where is it? 100%. Sometimes the computer just kind of covers up little things and leaves a couple little details out, but this works out 100%. Of all the neon, 90.48% is neon 20, which has a mass slightly less than 20. The reason that it's a little different is very complicated. And amongst friends, we can just say 20 AMUs is close enough. But when you have digits like that, they give you the mass. We're going to use the actual masses to do the calculations we're going to do. But 20 is close enough. Now, there's 3 isotopes of carbon. There's carbon 12. Now, does that make sense? Sure. Look at the key. Key is carbon. Same box as a little one. The average weighted atomic mass is 12.011. So the most common isotope would be carbon 12 because the mass rounds closest to 12. But there's also carbon 13, and then there's also carbon 14. Now, what you're supposed to do here is figure out how many protons and electrons are in carbon 12, carbon 13, and carbon 14. Well, carbon is atom number 6. It's the 6th atom. It's got 6 protons, 6 electrons all the time. Every single atom of carbon in the whole universe has 6 protons. In fact, every atom in the universe with 6 protons is carbon. That's how you can look at it differently. And if it's got 6 protons, it's got to be balanced with 6 electrons. So all the isotopes of carbon have 6 protons and 6 electrons. All the isotopes of any element have identical numbers of protons and electrons. What's different is the neutrons. So if your mass is 12, carbon 12, and take 6 protons away, you got 6 neutrons. If your mass is 13 and you take 6 away, well, you got 7 neutrons. And carbon 14, look at this. Carbon 14 would have 8 electrons. Now, something bright red in that top row. Carbon 12, carbon 13, carbon 14 is unstable. What the heck does that mean? Carbon 14, even though it only has 2 extra neutrons, the ratio of neutrons to protons falls into what's considered to be an unstable zone. Right? 8 to 6, that doesn't feel good. 7 to 6 or 6 to 6 feels good. 8 to 6 doesn't feel good. Makes the atom unstable. And what it wants to do is kind of like you, if you eat like 7 slices of pepperoni pizza, what do you get? You don't feel good. You want to spit it out. You're going to puke, right? That's what happens. Carbon 14 is unstable. And what does it do? It spits out part of its nucleus as radiation in an attempt to change that ratio to something more stable. That's what being radioactive is. The only difference between these 3 isotopes of carbon is the number of neutrons and the mass. The mass is so little, it doesn't really matter to you or to me, but it matters. And the reason it matters is because of the number of neutrons to protons, the ratio. Now, it also says here that out of all the carbon, 98.79%, with 4 significant figures there, is carbon 12. Only about 1% is carbon 13, and only about 1/100%, what is that, 11,000ths%, is carbon 14 and unstable. That's not very much, but it's radioactive. It's easy to measure. You have machines that can measure radioactivity, so it's easy to see in a sense. You can't see it, but it's easy to measure. Now, how do we figure out why carbon has a mass of 12.011 AMUs? That's what's called the average weighted atomic mass. It's not 12 plus 13 plus 14 divided by 3. That would be 13. It doesn't have a mass of 13. It has a mass of a decimal just a little over 12. It's just a little higher. You know why? Because most of it's 12, a little of it's 13, and even a little less is 14. So that means if we weight it, if we say most of it's 12, but some of it's 13 and very little of it's 14, what's the average of all of them? It's a little higher than 12. How do we figure that out exactly? It's a simple mathematical concept, and I'm going to teach it to you right now. The mass of all the isotopes makes up 100%. That's obvious, right? You have to know the proportions, right? It's not going to be 13. I need you to copy this, all right? Now, this is kind of a casual. We're using 12 AMUs, 13 AMUs, 14 AMUs. We're not using the actual atomic masses. Remember I talked about how they're never quite exactly so, but we're friends and we're going to have fun here. Most of carbon, how much of carbon is got a mass of 12? 98.79. So look what I did. I took the mass, 12 AMUs, and I multiplied 98.79% comes out to be 0.9879. If I multiply that across, I get that number, 11.8548. Now, I also have an isotope with 13 AMUs, and it's 1.10%, which means I can multiply it by a decimal that represents that as 0.0110. And that gives me the, 0.143. And then the isotope that's really little, the 14 AMUs with the very small percent, that's 0.0011, and that equals when you multiply it across. So the total mass is mostly the top one, a little bit of the next one, and very little of the next one. And when we add it up and we round it a little, we get 12.01. Now, in real life, there's a lot more decimal places. It's not really 12. It's probably 11.9979 or something like that. There's reasons why the atomic mass is a little bit casual here, but there's a lot more significant figures in the math, and most of them are a little bit less than the casual AMU number. But this is what we do. We take the proportion of each isotope, we multiply the proportion times the mass, and then sum them up to get what's called the average weighted atomic mass. Average weighted atomic mass is the mass listed on a periodic table. They take into account all the masses of all the isotopes and, importantly, the proportions of those isotopes. Scientists literally, there are people who say, what's your job? I go out and I measure elements. I go to different countries and I go to different continents and I go to different science halls and I say, show me your copper, show me your gold. And I'm going to measure, measure, measure. And I have very good instruments and I can figure out which isotopes they are. And I can measure what proportion is this isotope? What proportion is that isotope? What proportion is another isotope? Did I find a new isotope? And there are scientists that go around all the time. And literally every 4 years they get together in France because it's a great place to go. I've never been to France. I would love to go to France. But anyway, they go to France. They're in the International Union of Physical and Applied Chemists, IUPAC. And they present papers like, hi, my name is Charlie Busso, and I've been measuring copper all over the world. And although we know copper has a mass on the periodic table of 63.546 AMUs, and there's probably a lot more significant figures, my survey of copper throughout the world indicates that that number should be changed by 100,000th of a decimal, and then they argue about it. They decide, is Charlie right? Is Charlie wrong? Did he measure wrong? Let's measure again. The numbers on the periodic table are not all set, right? If somebody found a big copper mine in, I don't know, in Cuba, I don't think there's any copper mines in Cuba, but if they did, all of a sudden they got this big half a mountain full of copper. Well, maybe in Cuba, maybe in that copper mine, they have a slightly different proportion. If it's big enough, maybe it actually affects the average weighted atomic mass a little. These numbers can be changed. It's always based on the science. What's the truth? So every 4 years, the scientists get together, they argue a little, and every 4 more years, they come back and they argue some more. And every once in a while, some of the numbers on the periodic table, they could change a little. Not too much, not much at all, but maybe a little. It's always about what is the proportion of all the isotopes. And then they do a mathematical figure on it. Okay. This is a new element. It's not true. This is a fake math problem, but I like it, right? Because wouldn't it be cool to have an element named Arbuso? First of all, we need an A on the periodic table. We have argon, AR, but we can't spell any words without just the letter A. So many words we could spell. So we get a new element and we name it after me. I didn't find it because I'm a teacher. Maybe one of you is going to be a chemist and you could find an element, you name it after me. That would be fabulous. It would really be cool. The truth is you can't name an element after somebody who's alive anymore. There was an element, let's see if I can see it on my table. 106, it's called Seaborgium, named after a man named Seaborg who discovered it and said, I'm going to name it after myself. And they literally had a fist fight about this. You can't name an element after yourself. You're alive. He's like, I discovered it. I'll name it anything I want. Well, now the rules are you can't name it after yourself or anybody else who's alive. So if there ever was an element named Arbuso now, I wouldn't be here. I'd still be Zoomed maybe. Maybe these Zooms will be here forever. Teaching. Maybe I'm alive now, but maybe when you're watching this in the future, 50 years or 100 years, maybe there'll be an element named Arbuso. So there's 2 isotopes. We call them element A58 and A59. Arbuso mass of 58, Arbuso mass of 59. As it turns out, 92.08% of all this Arbuso element has a mass of 58.02 AMUs, which is not 58, it's a little different, right? We're going to use the actual atomic mass units. The rest, I don't tell you how much, right? It's 100 minus 92.8 is going to be 59.03 AMUs. So when you're presented with the casual A58 or the mass 58.02 AMUs, we're going to use the 58.02. The difference is probably not going to be noticeable, but correct is to use the proper atomic mass unit. So when presented with both, we always use that. We wouldn't use 58, we use 58.02. So what is the average weighted atomic mass of this cool, right? It was named after me, cool new metallic element. You do this. I'm going to wait. I'll think of a joke. So, I just thought of a very funny joke, but you wouldn't get it. And I thought of another funny joke. A lot of chemistry jokes, you got to wait around a little. You got to learn a little more chemistry. You got to learn about what is an ion. You got to learn about things before they're funny, right? So I'm just stalling. Hit pause. I don't have any jokes. Figure out how to do this, right? Here we go. 58.02. And since 82.08% of it has a mass of 58, we change that to a decimal, 0.8208. So you multiply the mass times its proportion, and then you multiply the other mass, which is 59.03, times its proportion. How did we get that 0.1792? Well, if 82.08% of all this stuff is one isotope, the rest, well, all of it's 100%. If 82.08% is busy, the leftover part, that's the 17.92%. So when you multiply this across and then add it up, this atom, this make-believe atom, has an average weighted atomic mass closest to 58, but it's actually 58.1365 AMUs. Now, it says on the bottom, when the casual mass 58 and 59 are used, the numbers are going to be almost exactly the same, but it's not correct. This is more correct. This always use the right numbers. Now, does this make sense? The average weighted atomic mass rounds to 58. Is the most common isotope 58 AMUs? Sure it is, right? It's 82%, a little more than 82% is 58.02. Of course, that's how it works. That's why it works. Whatever's the greatest proportion has the biggest impact on the overall average weighted atomic mass. So this make-believe isotope with two isotopes, one atom, one kind of atom with two isotopes, this is how you figure out what's called the average weighted atomic mass. The reason the numbers on the periodic table for atomic mass have decimals is not really because the masses, it's a whole number of protons and neutrons. It's really more about the proportions. The proportions are exquisitely measured to a lot of significant figures. So, unknown element X has three isotopes, X23, X24, and X25. The first isotope is 75%, the second isotopes make up 20%, and the last isotope is 5%. We don't know the actual atomic masses here, so we're going to have to use the casual 23 AMUs, 24 AMUs, 25 AMUs. This is a concept. This is a concept. We're not really, there's no such thing as element X, right? There's no unknown elements. There's 118 of them. They're all known. If anybody finds a new one, it'll be happy days are here again, and we'll all read about it in the New York Times. This is a math problem. So this is more, can you figure out how to do the math? Now, it's the same thing, except there's three lines instead of just two. There's three isotopes. So it's going to be 23 AMUs times 0.7500. The first isotope, 23 AMUs, 75%. Then it's going to be 24 AMUs times 0.200. And then 25 AMUs times the 0.050. The column in the middle, 75%, 20%, 5%, that adds up to 1.0. That makes good sense too, 100%. And this stuff, 23.3 AMUs average weighted atomic mass. Now, does this make sense? Sure, it makes sense. The most common isotope is X23, has a mass of 23. 75% of this stuff, X, has a mass of 23. The average weighted atomic mass is closely rounding to 23. It makes perfect sense. Get in black at the very bottom. There's no scientific measurement for the mass, so you can use the casual isotope numbers as the AMUs. Most of the time, there's going to be an actual average weighted atomic mass. Sometimes the region says it like this, and so you do easy math instead of decimal math. It's all the same. It's in the calculator. It's the mass of the isotope times its proportion equals, plus the mass of another isotope times its proportion equals, times the mass of as many isotopes as you got times their proportions, and then you sum them up, and that's how you get the average weighted atomic mass. I think that's it. Yep, we'll be done. These are not hard. There's some homework problems. You got to get on that. Peace, love, and chemistry.